Hi there, this is Group 4. Our project topic is malleability attack on Bitcoin transaction theory and practice. This will be presented by Zheng Lingling, Chen Zheke, Chen Li, Xu Dan, and me, Chen Jinhong. Here is the content of our presentation. We'll firstly do a brief introduction about Bitcoin payment system. Then we'll focus on the definition and practice of malleability attack with a live demo. We'll then demonstrate how the problem be caused and be solved. So at the very beginning of the video, may I have you guys think about the question, is Bitcoin safe? Well, before I answer this question, maybe it's a good thing to take a look at the breakdown of Bitcoin and their transaction. So Bitcoin is a payment system that was introduced as an open source software in 2008 and released 1 year later by a developer named Satoshi Nakamoto. The core feature of this system is that decentralization, which means all the activities regarding planning and decision making are delegated to all individual participants instead of an authoritative institution. So how attractive this feature is? Maybe the price rising of Bitcoin within the recent year is one of the answers. Now let's start our journey of a Bitcoin transaction. As this is a payment system, how will an exact payment be done within the system? Well, let's say Alice and Bob are two Bitcoin players. Alice will transfer 5 Bitcoin to Bob. In order to do so, Alice put down the details of this transaction. She signed on it with her private key and used hash function to translate all of this into a collision-resistant string, which is a unique ID. In this case, let's call it transaction ID 1. This transaction will then be collected by Alice's node and set accessible to other nodes in where we call it as mining pool. There are other transactions being sent by other nodes, including in this mining pool. All of these transactions are waiting to be verified and confirmed. Okay, so who will do the verification work? The answer is miner nodes. Within the pool, every miner node will collect some of the transaction and verify them. Lots of things will be checked, including the balance and signature of the senders. Once the transaction is verified, it will be stamped a Merkle root like a fingerprint and stored temporarily. Now it's time to see who's going to let everyone know these stamped transactions, as there are many miners here. To do so, all miners will do a job called proof of work, like overcoming the challenge. The first miner who did it will broadcast to other miners and get verified. Once all of this is done, that means all transaction has been confirmed and packed up. This is what we call a block and a blockchain. Wow, looks everything all good. It is quite a safe system, isn't it? However, in 2014, one of the major Bitcoin agent platforms named Antigox got bankrupt due to a hacking. The hacking was conducted within only 1 month, and the loss was absolutely numerous. As per what Antigox claimed, they were under a malleability attack, which caused the majority of their loss. Well, now is the time to rethink about the question I mentioned before. Is Bitcoin safe? If not, how does the malleability attack make it unsafe? Well, let's get back to the process that I mentioned before. This is where the malleability attack takes place, which means the attacker will do the bad things before the transaction gets into the mining pool. Hereby, I'll pass to my teammate Zheng Lingling to show what exactly happened in this place and what exactly happened with Antigox.
So how is the transaction malleability happened in Mt. Gox? This is the case. Mt. Gox received a withdrawal application from client Bob. Bob is a client as well as the attackers in Mt. Gox. So Mt. Gox generates a transaction, and after signing the transaction, the hash of the signature and the transaction details, TXID1 here, would be used as the transaction identifier. The worker node would receive the transaction and pass it to the mining pool. But if the transaction is received by malicious node, the red node here, that's controlled by Bob, Bob would replace the original signature, and the modified signature is also would be valid. But the transaction ID would change to TXID2 here. So how both transactions enter the mining pool? For some reason, if the modified signature is first mined and converted in blockchain, then the original transaction would be abandoned based on the Bitcoin UTXO mechanism. So in the end, Mt. Gox actually completed the transfer to the Bob, but cannot convert the transaction under XID1 here, the platform no. Then Bob would claim that, oh, I didn't receive the withdrawal money and request a new withdrawal. The Mt. Gox would make a wrong decision, then send a new transaction to Bob again. This would lead to the double pay. Based on the explanation before, we see transaction malleability is by modifying signature, which leads to the change of T transaction ID. The modified transaction would be still valid, but cannot be checked by original transaction initiator. Now, I would like to invite Xudan to introduce malleable signature.
So according to the above, now attacker can change the signature but without invalidating it. This is a malleability attack. Then you may ask, why would a changed signature be valid? In fact, whether a signature is valid depends on whether it can pass the verification. However, some signature algorithms, such as the signature scheme ECDSA for Bitcoin, they have the feature of malleability. ECDSA stands for the elliptic curve digital signature algorithm. We can see that the elliptic curve is symmetric over the x-axis. Here during the sign process, we have 3 math formulas for the signature generation, but you don't have to really understand them. We first need to know the meaning of these notations. Key here is a randomly chosen number, C is the message, D is the private key, and the capital R is a random point on the curve. The small r is the x-coordinate of the random point R module N. So the biggest takeaway of this sign process is that the signature pair RS is finally generated. Now let's move to the verification stage. There is also a math formula that looks quite complicated. We just point out that Q here is the public key and G is the generator point of the group. Once the verification returns true, we will accept the signature. So is there any flaw during the sign and verification processes? Then I will pass by Kyle to present more on this process.
Now let me talk about the flaws and do a demo. Actually, there are 2 discovered flaws. The first flaw is the yellow padding in signature DER encoding, and the second flaw is the low S and high S in ECDSA verification. Now let's go into detail. We know that the signature of ECDSA is just 2 big integers, R and S. In order to pass this signature through the network, we need to encode them into bytes. In Bitcoin, it used DER distinguished encoding rule to encode the signature. Let's look at this graph. The yellow box is just 1 byte of special symbol that can use for decoding, and the L is the length of corresponding data. The first L is the length of this data, and the middle L is the length of R in bytes, and the last L is the length of S in bytes. So how does the first flaw work? Here is the original DER encoding, and the attacker can add 1 byte of yellow padding in front of the R. Because R is an integer, so adding yellow in front of it, the value remains the same. And here we add the L by 1 for the length. Bitcoin used OpenSSL for the DER encoding, and OpenSSL did not strictly verify the DER encode data by default. Therefore, this yellow padding can pass the signature verification. In order to fix this flaw, there is a Bitcoin Input Proposal 66, which mandates a strict set of rules to how the DER data is encoded. Now let's go to the second flaw. In the ECDSA sign and verify process, we only use the S coordinate of the arrow point in the curve. And because the curve is symmetric, there will be 2 arrow points can satisfy this S coordinate, and it will lead to 2 corresponding S can satisfy this verification formula. In other words, if R and S is a valid signature, then so is the complementary signature R and minus S mod N. So the attacker can change the transaction signature by change the S to minus S mod N, and it can still be verified. In order to fix this flaw, there is a pull request 6769. It enforced using low S value. And by the way, another blockchain level Ethereum is also using ECDSA. Ethereum input proposal 2 also enforced using low S value. Now let's look at a demo of attack and fix. In this demo, we're sending Bitcoin from one wallet to another. We made a transaction and print the information. Now we can see we are sending this amount of Bitcoin from this wallet to this one. We suppose the transaction was received by a malicious node. In this malicious node, the attacker will use yellow padding to change the signature. Here is how the attacker can add yellow padding in front of R. And we'll print the modified transaction. You can see that the transaction IDs are different, and the modified transactions can pass the line strip verification. Then we broadcast the modified transaction into the Bitcoin network. We got an error, line canonical DR signature. So the fraud cannot work. Now the attacker will try to use high S to change the transaction signature. Here is how the attacker can change the S to high S. Again, we print the modified transaction information. Here we can see the modified transactions and the original transaction IDs are different, and the modified transaction can pass the line strip verification. And we will broadcast the modified transaction into the Bitcoin network, and we got an error. S value is unnecessarily high. Therefore, these two floats are no longer work. Here, my question is, if there's some hidden fraud, how can we solve the transaction malleability permanently? In order to answer this question, I will pass the control to my teammate, Chen Li.
Bitcoin's developer adopted a very intuitive way to solve malleability attack. When generating the transaction ID, it will not include the signature into the hash function by leaving the field blank. Instead, signature was put into a new field called witness. In such a way, blockchain has everything it needs to verify the transaction. More importantly, transactions identifier won't be affected by signature. Whether or not it might be malleable, it no longer impacts the only thing it impacted it before, transaction ID. Although SegWit solved malleability attack, a lot of miners did not like it, and they chose not to update the software, which in turn caused a fork of Bitcoin Cash. One unconfirmed guess is that it could make their costly, specifically designed mining machine useless due to the new mechanism of witness Merkle tree. In conclusion, signature malleability is a side property of the signatures algorithm, which will not weaken the security of digital signature. Malleability attack in Bitcoin was caused by the mechanism generating the transaction identifier. Actually, Bitcoin's developers knew the malleability of signature from very early stage, yet they only decided to fix the problem after Mt. Gox claimed its loss was mainly because of it. The main reason was that malleability attack by itself was seen as a harmless trick which cannot falsify any part of the transaction, cannot double spend Bitcoin, only causing some trouble for wallet confirmation. And if client's wallet frequently updates its database, it will notice its original transaction has been confirmed. However, the reality is different from developers' view, since the users are not that tech-savvy or aware of all the vulnerability of the system or all the precautions needed to be taken. Even after the developer provided a secure solution, users might still not want to use it. This leads to our final conclusion. To reach cybersecurity, the trade-off between what developers want and what users want is the crux that needed to be taken care of.